a month or so. So today, Tim is going to talk about fundamental dynamics for quantum theory. Why complex numbers?
Yes. Okay, so before I start, there's a rant I need to get on. I'm now probably going to give this rant before every talk I ever give. I'll go through that quickly and say some other things. Let me just say first, for people who don't, who don't feel technically like at home with this stuff, all I'm going to do is point at some equations and notice similarities. You don't even have to understand what the equations say. Say, look, this looks like that. Okay, that's really all you need to follow. First part. Second part, if you know all this stuff, if nothing else, I think there's some history here you probably don't know on the basis that I didn't know it 8 months ago. And it's really interesting. So there's some nice history, I think, even. Third point, when I saw Craig's title, I thought maybe we'll be saying the same thing. No, we're saying completely different things. So I thought maybe I can just say, oh, what Craig said, and then go on to something else. This is going to be a completely different story. Now
hopefully it's both, they're both true.
Complementary. Now the rant, which is just a fact, right? Sociological fact. When you learn physics in high school, in college, whatever, you learn physics by learning Newtonian dynamics. You usually learn calculus in the course of doing that, right? You understand differentiation, integration, applying it to Newtonian mechanics. You imbibe Newtonian mechanics with your mother's milk. And I want to tell you, Newtonian mechanics is poison, okay? You've been addicted. You've absorbed a lot of conceptual structure that you don't even realize is there, and you bring it everywhere, okay? And a lot of this talk is going to be trying to wean you off of, cure your addiction to Newtonian mechanics, okay? But it's a methadone treatment. I'm going to give you a replacement for the addictive thing, which is actually also classical mechanics. It's not that I'm going to jump to quantum mechanics. Quantum mechanics is in here, but I'm going to give you classical mechanics, classical electromagnetic theory, which you may already have some familiarity with. I'm going to ask you to start thinking in those terms. Okay? So I can't blame Newton for what we do with Newton, but I think it really messes everything up. That we come to all kinds of questions with this Newtonian background sitting in our heads that we can't easily dislodge. So a lot of this is trying to dislodge. Now let me say something nice about Newton, about actually not his theory, but his methodology, right? The heuristics of what Newton did self-consciously. He claimed to, and will be upset at the word he used, deduce his theory of gravity from the phenomena. But we know he didn't deduce it in the logical sense that the phenomena, right, logically imply his theory. But nonetheless, you could say he was very interested in motivating his theory from phenomena, right? So I think that's a great idea, right? I think that's a wonderful idea. Start with some iconic physical phenomena to get you into the theory. Now, as I say, he said he deduced it. He didn't mean derived it logically. You know, it's just we use that to deduce. And not only did he not deduce the thing in a logical sense, he also, even in the Principia, the fundamental dynamical equations, he just postulates, doesn't attempt to deduce, right? F equals ma, essentially. It's just given that, then some observations, what he deduces is this universal inverse square law for gravity. But I think it's a great idea, right? Even though he didn't deduce and blah, 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 I think this is very powerful and it's what we should be doing. You start with some observed phenomena, you motivate your theory by considering those phenomena and asking yourself, well, how could I account for that? It's very against this kind of pure hypothetico-deductive thing that I just, I go to sleep and in a dream, some equations come to me and I say, well, postulate those and see what happens, right? I mean, you can do that, but I don't recommend it. Okay. Of course, we want to do this for quantum theory because we know Newtonian mechanics is wrong. It's just wrong. It's false. A bunch of physicists will tell you, no, it's not false. It's just restricted. No, it's just false. It's false everywhere. So we need to do this for quantum dynamics. And how do you get to quantum mechanics? Well, there's this kind of method that people are sort of familiar with, where you say, well, first write down a classical theory, meaning a Newtonian theory, usually. And then you've got these variables, x and p, and then you put the hats on, right? This is Detlef Durr used to talk about the Mad Hatter, right? Put the hats on, turn the variables into operators, have you blah, 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 blah. That's all kind of crazy, right? I mean, that just makes no sense. Why? Because the classical theory you're starting with is wrong. You're not going to cure its wrongness by putting hats on. Okay? So that's the wrong idea. I want to go back to this idea. Let's look at some phenomena. Let's think about how we might explain them. Let's try and get at things that way. Now, there's another fact about quantum theory that's often been observed by many people. I'll have some quotes, which is that when you write it down, it's in terms of using complex numbers. The psi function is a complex function. And many people have just thought, that's weird. You know, just kind of, where'd that come from, right? Who ordered that? And the most famous example of this, I guess, is in this essay of Wigner, where everybody at least knows the title. I'm not sure how many people have read it. The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Now, Wigner says there are some pieces of mathematics that it's pretty clear how they're connected to physics, like basic geometrical notions, which arose from trying to deal with space in your everyday life. But other parts of the mathematics he found very, very puzzling. And so here's the quote from that. Let us not forget that the Hilbert space of quantum mechanics is the complex Hilbert space with a Hermitian scalar product. Surely, to the unpreoccupied mind, complex numbers are far from natural or simple, and they cannot be suggested by physical observations. Notice, right? I can't look at something and say, ooh, complex numbers. Furthermore, the use of complex numbers is, in this case, not a calculational trick of applied mathematics, but comes close to being a necessity in the formulation of the laws of quantum mechanics. Finally, it now begins to appear that not only complex numbers, but also analytic functions are destined to play a role in the formulation of quantum theory. The thing about analytic functions, but you see, he just raises exactly this question: why the heck are complex numbers showing up in this theory? Now, there's another thing that puzzled people early on, which is that the fundamental dynamical equation of quantum theory that everybody starts with, maybe you modify it a little like Daniel does with a collapse part, but anyway, you start with Schrödinger's equation. And you just look at its mathematical form, it kind of looks like a diffusion. You'd already be familiar from classical physics. That's a diffusion equation. That's like the heat equation. I mean, Craig also noticed this. And in fact, if you go back and read when Schrödinger introduced the wave mechanics, it's this four-part paper, big four-part paper. And in the first three parts, he demands that the psi function not be a complex function, it's a real function. And it's only in the fourth part where he gets to dealing with time-dependent. So in the first three parts, you get what's so-called time-independent wave equation. And then in the last part, he says, well, I do have to deal with time variation in my potentials. And then he introduces this complex valued psi function. Okay. And here's just out of Max Jammer's book. People complain about Jammer. Maybe I would complain about Jammer, but anyway, I like this. He's just describing the situation. In the fourth communication, the last part of the paper, Schrödinger developed his theory of time-dependent perturbations, realizing that an equation, now this is the time-independent equation, 5.77, the eigenvalue E varies in passing from one stationary state to another, and consequently must not occur in what he called the real wave equation, Eigenbildungsgleichung, which is to determine the spatiotemporal behavior of the wave function psi of x, y, z, t, Schrödinger eliminated E, right? He couldn't, before the E's are kind of fixed in time, but now they're going to vary. So he needs to get rid of them. So he gets rid of them by this equation, and you'll notice, okay, I is now showing up. In the first three things, no I, no complex numbers, no imaginary numbers. Now, in order to solve this problem, you see e to the I. So that's going to give you cosine plus I sine. You're going to have a real and a complex part. This is where it's coming in. And then he gets what we all know and love, what we call the Schrödinger equation. Okay. We're gonna consider that equation in some detail in a minute. Schrödinger postulated the validity of the Schrödinger equation, later called the Schrödinger time-dependent wave equation, also for time-dependent potential functions. So now the potential is changing, and you can plug this in. Recognizing that an equation has the structure of a diffusion equation, so this is kind of like the heat equation, with an imaginary diffusion coefficient, right? So that's what we just saw back here. This is the coefficient, right? And now you've stuck an I that wouldn't show up in the heat equation, right? Wouldn't show up in a classical diffusion equation. You've stuck the I in, you made that imaginary. And Schrödinger realized relaxed his original requirement concerning the reality of psi and admitted complex value functions for what he called the mechanical field scale of psi. As an application of the time-dependent wave equation, he studied the phenomena of dispersion, which he treated as a problem involving a periodically varying potential energy function. But how do you feel about that? I mean, now there are a couple of things you say, wait a minute. First of all, why the heck are we talking about a diffusion equation, right? You think about the model in your head is a classical diffusion equation, like the heat equation. How does that work? Well, the heat equation works by basically saying, here I have a distribution of temperatures. Calculate how the temperature at any point differs from the average temperature around it. And then the equation tells you this will move in the direction of the average, right? So if I'm a little higher than average in my temperature, I'll move down. I'm a little lower in temperature than my environment, I'll move up. And you just immediately see, okay, at the end of the day, everything's going to go to equilibrium, right? This is just going to naturally evolve to a stationary solution where the temperature is the same, thermal equilibrium. Right? That's what you expect from that kind of equation, and that's what happens. But what the heck does that have to do with the Schrödinger evolution, which doesn't look like that at all? And furthermore, what the heck do you mean I'm just going to take my classical diffusion or heat behavior and stick in an imaginary number, which is the number that's characterizing how fast this occurs, right, in the classical setting? So, this is all just very, very puzzling. Wigner would have immediately said, where the heck did I come from in that? And what I want to do is walk through this whole problem from an entirely different point of view and explain why we're getting these complex numbers and explain why the Schrödinger equation has the structure that it does from an entirely different point of view. Now, another nice quote. As I say, this happens, the first three parts of this paper of Schrödinger, it's a real psi equation, keeping things real. And then in the fourth part, he's forced to this imaginary psi. And if you go to, this is literally the last paragraph of that fourth communication, and you'll just hear how Schrödinger felt about what he did. Meantime, there's no doubt a certain crudeness in the use of a complex wave function. If it were unavoidable in principle, which is more or less what Wigner claims, and not merely the facilitation of the calculation, this would mean in principle two wave functions, which must be used together in order to obtain information on the state of the system. This somewhat unacceptable inference admits, I believe, of the very much more congenial interpretation that the state of the system is given by a real function and its time derivative. Notice the contrast here. If I take this seriously, there are two waves. But I think really that's not what's going on. There's the initial conditions are, as in classical mechanics and classical Newtonian dynamics, the positions and the time derivatives, right? The positions in the momentum, positions in the velocities. Our inability to give more accurate information about this is intimately connected with the fact that the pair of equations here we have before us only the substitute, extraordinarily convenient for calculation to be sure, for a real wave equation of probably fourth order. That's not that, I mean, I thought he meant fourth order in time, but anyway, second order in time. Other orders in spatial derivatives, which, however, I've not succeeded in forming for the non-conservative case. So that's where he wanted to go. That's where he thought you have to go. It didn't go that way, right? We now just postulate the complex valued wave function. We postulate the fundamental Schrödinger equation. We do everything in those terms. Schrödinger himself would have been scandalized or upset anyway. No. This was just a little stepping stone to a better thing. Okay, so here we are. Where are we? Now have two formal features of the Schrödinger equation that are prima facie surprising. One, it contains I, the imaginary unit, and it describes the dynamics of a complex function psi, not a real function psi. And the second thing is that it's an equation that's first order in time. That is, there's only one time derivative in it, right? It's just ddt. Whereas in Newtonian mechanics is a second order theory. The fundamental dynamical equation is d2, dt2, right? It's about accelerations. It's because the fundamental Newtonian dynamical equation is about accelerations that the initial conditions have to be both positions and velocities. Okay. And so anyway, formally the equation that you have looks like a diffusion equation with an imaginary diffusion coefficient, but you don't understand what the heck that even means. And so we have both, this description is strange because we have the imaginary numbers and because you're making an analogy to diffusion behavior and we are not looking for diffusion behavior. So let's go back to the beginning. Can we explain all this? Can we motivate? Now, when I say motivated, imagine you've got a palette of fundamental dynamical equations that you're already familiar with. And you're now doing quantum theory and you say, which one of these should I take prima facie as my model? Let's just look at a few equations you would have if you just had done Newtonian mechanics, classical physics up to the time of quantum mechanics. Well, as I said, of course, we're all familiar with IAPT9. A is itself the second derivative of Q. That's what I mean by saying there's a second order equation, second order in time, right? Second time derivative. So you'd be already familiar with that guy. You would have also been familiar with a kind of reformulation of it, where now this basic equation of F now is first order in time, one derivative. But what it's the derivative of is this P, the momentum, but the P itself is another time derivative of Q. So this is just kind of a way of hiding that it's second order by breaking it up that way. Okay, you'd be familiar with that. And in that equation, m is a constant. That's essentially tells you that the momentum is just the mass times the velocity. You might say, well, gee, here what I have on the surface are a pair of linked first order equations, right? Two equations linked. Here I have a single second order equation. But you might say, yeah, okay, fine. Really what's going on is this. This is just a kind of convenient way of representing. But there's some other equations. We talked about the heat equation, all right? So what does it look like? Just again, mathematically, it's just this guy. First order in time, a single derivative in time. How this U function, that's the temperature function, changes with time is some constant alpha times the Laplacian of U. The Laplacian is a spatial derivative. It talks about how things vary not in time but in space. It's second order in space, x, y, z. Yeah? But it's a spatial derivative. So that you've got that guy. But I already told you what that guy does. That guy takes my field, and if it's bumpy, it evens out the bumps, right? And goes to equilibrium. But, of course, if you're familiar with that, and here's Schrödinger's equation, you say, well, look, here I've got first order derivative, okay, some constants. There's the I sitting there. Where did that I come from? Okay, some constants, some other constants. There's your Laplacian again, Laplacian's I, right? Then you have this extra little piece, the potential piece. But you could look at that and say, yeah, looks kind of like the heat equation with an extra little gadget on it. Here's another equation we've taught that was even mentioned, that Daniel mentioned. The incompressible Navier-Stokes equation for a fluid of constant density. Notice again, don't worry about it, just note, du dt, oh, alpha Laplacian u, oh, alpha Laplacian u. Okay, so those pieces are literally identical. And then you'll have these other three pieces, kind of complex pieces. This is a gravitational constant. There's a bunch of other stuff that comes in here. But one thing about the Navier-Stokes equation, which you know, even if you haven't studied it, I really never studied it, but we all kind of know, it's fluid dynamics, right? This is what you use to describe water waves. And so it gives you wave behavior, right? So that's interesting. But again, this A here, this well, no, it doesn't even show up. There's no I's in this, right? There's nothing imaginary. The other thing about the Navier-Stokes equation is nobody thinks it's a fundamental equation, right? It's not. It's a derivative equation. It's supposed to be an equation that approximately describes, in a certain regime, the behavior of water described at a certain level of approximation, and that there are cases where it will break down, as Daniel said. In the ocean, when you have crashing waves, they're not described by the Navier-Stokes equation. Absolutely not. So, in a way, it's there mathematically, but if you're looking for a kind of paradigm fundamental equation, it's not a good candidate. Nobody thinks it's a fundamental. And finally, now this is again my methadone, something you're probably familiar with. Maxwell's equations for the electric and magnetic fields, which Maxwell didn't write them this way, but here they are. Look at those. This is for the free fields, so I have no charges. Okay, so free electromagnetic. Pair of equations. I have two fundamental quantities, the electric field and the magnetic field. These are both first order in time. The change in the electric field is somehow determined, again, now this is my saying Laplacian, somehow controlled by the spatial distribution of the magnetic field, and the change in the magnetic field is controlled by the spatial distribution in the electric field. And these are a pair of linked equations because B is controlling the time evolution of E, and E is controlling the time evolution of B. So there's this mutual. Now, so those are a bunch of models that you might start with, saying, I have some phenomenon I want to explain, where should I begin? Now the question is, okay, what's the phenomenon? What physical phenomenon should I look at to motivate my choice of one of these as a model? And I now want to say we're going to do something that's completely unhistorical, totally unhistorical. Not the way quantum theory was developed. You know, quantum theory sort of first came out in 1905. Well, came out of black body radiation by Planck, and then in 1905 from the photoelectric effect, and then eventually by the stability of atoms and radiative spectra and so on. But that's not the way we teach it for good reason. When we teach it, we start with a different phenomenon that was not historically important. In fact, a phenomenon that was only looked for historically once the theory was in place, namely two-slit interference. Interference, single particle interference phenomenon. Okay? Standardly two slits because it's easy. This is what Davison and Germer finally checked this by bouncing stuff off of crystals. But that's after the theory's developed. Now, what do we know about two-slit interference? We, as it were, take electrons one by one and throw them at a screen with two slits in it, and we look for the pattern at which these dots form on the screen behind. And you can do that in a lab, and you see interference bands. I'm sure everybody's familiar with that. Here's Bell's very kind of famous comment about this. This is in 6 Possible Worlds of Quantum Mechanics. The last unromantic picture I'll present is the pilot wave picture. It's due to de Broglie and Bohm. While the founding fathers agonized over the question, quote, particle or quote, wave, erase the quotation. De Broglie in 1925 proposed the obvious answer, particle and wave, right? There's a wave part of the ontology, and there's a separate particle part of the ontology. Is it not clear from the smallness of the scintillation on the screen that we have to do with a particle, right? Something's hitting the screen. And is it not clear from the diffraction and interference patterns that the motion of the particle is directed by a wave? Now, when Bell makes this comment, he's of course introducing the pilot wave theory, and he's really focusing on the particle part, because standard quantum mechanics doesn't have particles. And every version of quantum mechanics has a wave function in something like Schrödinger's equation. But I want to do the other thing. I want to focus on the wave part, right? Doesn't the phenomenon, doesn't the interference bands, don't they indicate something is behaving like a wave? Right? It's showing wave behavior. And not only is it something, unlike the Navier-Stokes equation, if you think of the Navier-Stokes equation, what does it describe? It describes a huge number of particles in the ocean. It's a huge collective behavior. But here, we're just taking a single electron in what's otherwise a vacuum, throwing it at a screen and seeing a dot. Throw another one, see a dot. There shouldn't be a huge collection of anythings, right? This wave behavior is somehow very deep in the fundamental dynamics. Okay. So waves in what? Now, it's of course, reminiscent of light, this interference effects. Two-slit interference of light was demonstrated and known, and certain interference effects of light were what pushed people from a particle to a wave theory of light. We know how that happens in the classical theory of light, namely Maxwell's equations, because you have this dynamics of these two fields, the electric and magnetic fields. And of course, when all this started with the wave theory, the classical people were so stuck in their, again, Newtonian mechanics was so stuck in their heads that they said, gosh, what are these waves? What are these? They must be stresses and strains in a medium. I need a mechanical picture of the luminiferous ether. I need to think of the luminiferous ether as a bunch of particles connected by springs or something, all governed by Newtonian mechanics. And when I wiggle this one, okay, the wiggle goes along. And where we finally made progress was to say, no, these are, as it were, displacements or changes in something very non-Newtonian, a field. It's a different kind of gadget, right? It's a different ontological physical posture. There was all this looking for the effects of the medium, as we know, looking for the Michelson-Morley experiment and stellar aberration, blah, blah, blah. Never found any sign of a medium. You couldn't even come up with a theoretical picture of a medium, Newtonian medium that did what they wanted it to do. Eventually, what do? You do the right thing. You say, forget that. Just accept E and B as new fundamental physical postulates. They're fields. They're not particles. They don't, how do they behave? Here are the equations. And so my point is that wave dynamics, wave behavior, that is, what I mean here is specifically constructive and destructive interference, is fundamental. It's built into the basic dynamics. In Maxwell's theory, it's not emergent as it would have been in the Navier-Stokes equation. Good. So Leave aside the particle. I'm not going to talk about the particle. This doesn't, you might not believe in particles. You may not like the pilot wave. I don't care. That's not what this talk is about. It's to talk about Schrödinger's equation and the wave function. So we know that there's something behaving like a wave. We want to postulate, we want some fundamental dynamics that will get us that. Given our model dynamical equations, what are the prospects? Well, now I'm just going to say things that follow immediately you probably already understand. Of course, in Newtonian mechanics, I can kind of get wavy behavior in liquids or elastic media, vibrating strings, particles with Hooke's law, springs attached to them, okay? But that's accounted for by Newtonian dynamics, but only because I have specified a very specific situation about what the Hooke's law is or the elastic medium and blah, blah, blah. And it's not built into F equals ma per se, right? The only way to get this wave behavior in a Newtonian setting is to postulate a medium, material medium, and a bunch of physics of the medium. We don't want to do that because, again, you can do two-slit interference in a vacuum. Ain't no medium, ain't no mechanical medium there. Well, the Navier-Stokes equation, again, that'll give you some wave equation. That'll give you constructive and destructive interference. But first of all, those waves are nonlinear. They're complicated. They depend on the depth of the fluid. They depend on the amount of the force of the gravitational field. This is just not anything like what you want as a model for a fundamental dynamical equation. Again, that's, this is the Navier-Stokes equation. If I wanted to use this, oh, I know this gives me wave equation. Okay, but what's this piece? What's this piece? Especially, what's this piece? That's gravity. If you don't have gravity, you don't get waves in the ocean, right? If you don't have gravity, the water starts to go and it just keeps going. goes into outer space. Okay. There are simpler Newtonian waves, of course, that you have if you idealize a perfect Hooke's law restoring force, if you idealize in a string that the restoring force has various properties. But those, again, are idealizations of elastic media. You wouldn't expect that a rigorous non-idealized treatment of real physical media like drumheads even to yield simple linear wave equations. They won't, right? There might be good linear approximations in some regime, but what we have in the Schrödinger equation is a fundamentally linear equation. That's what leads to the Schrödinger cat problem, blah, 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 okay? So I want to say Newtonian mechanics, fundamental Newtonian dynamics does not all on its own lead to anything like wave behavior, much less linear wave behavior. Not the heat equation for the reasons I said, because we know what it's sort of understanding this, the way you understand this classically is that the heat equation holds because you have a billion particles and they're kind of randomly colliding with each other and stuff is diffusing. And again, it's going to equilibrium. Nobody thinks the heat equation is a fundamental equation. What about electromagnetic waves? Okay, now we're cooking, right? Electromagnetic waves certainly show the kind of interference, the constructive and destructive interference we want. Of course, as I said, people started thinking, well, I need to have some elastic medium in which the waves are waving, and eventually we give up on that. We say, no, there's just the electric and magnetic fields. They're fundamental. They're not stresses and strains and something else. And we need some fundamental dynamical equations for them, and we know, I've already shown you what they are. Maxwell's equations. Three equations here. I mean, I could talk about the putting charges in, but just to make it. What is the now question? What is the fundamental character of these equations? What is the fundamental mathematical character of these equations? There they are up on top. Point one, they are both first order equations in time, unlike F equals ma, which is second order. So I have a pair of first order equations. Oh, crap. Yeah. And each links the time derivative of one to the time derivative of one to the spatial distribution of the other. They happen to do it in almost the same way, right? It's both curl of B and minus curl of E. That doesn't really so much matter. They have the same thing, so let's just call that reciprocal first order dynamics. I have two equations, two fields, each controls the time development of the other, reciprocal, and they're both first order equations. That gives rise to wave solutions. We know that. You know all this. Again, I'm going to go fast now, but you know this gives rise to electromagnetic waves, gives rise to interference phenomena, blah, blah, blah. Now, there's a very interesting point here, which I wish I had time for, but because it's a sidelight, I'll just say, there's a very nice paper that Hamilton writes in 1833, trying to give a unified theory of planetary orbits and light, optics, optico-mechanical unification. That's what gives rise to Hamiltonian mechanics. There's some really interesting story there. I'm going to skip it because it's a sidelight. I'll come back to it if you want to know. But you can compare the equations that drop out of Hamilton's approach, which are this pair of equations. Many people will be familiar with them. How Q is the momentum, how Q changes in time first order is some function of P. I'm sorry, Q is the positions. How they change in time is some function of P. P is the momentum. How the momentum changes in time is some function of Q. That will fall out of Hamilton's equations if the Hamiltonian divides into two pieces. One piece is it's merely a function of P, and the other piece is merely a function of Q. That's the same basic architectural structure. Okay? Now, in the case of Maxwell's equations, it's not just that this is some function of P and that's some function of Q, but the functions are very, very close to each other, right? If we drop the constant, they're almost the same up to a minus sign. And so it might occur to somebody to say, I can actually take these two equations and jam them together into a single equation. How? It's kind of trivial. Use complex numbers. Why does I come in? I comes in merely as a bookkeeping device to indicate whether it's E or B, right? I'll let B be the imaginary part of this complex field, and E be the real part of this complex field, okay? So you get a complex version, a presentation of Maxwellian free theory in terms of a complex field, single complex field, F, which the real part is the E field, and the imaginary part represents the B field. Okay? And the I's are just keeping track of them. Now, because what you can do, you just plug that definition in here, and you derive how this field will behave as a function of time. And it's very simple, right? And furthermore, in this fundamental equation that now gives me the behavior, this is the behavior of my complex field, you'll notice I's popped up here in the fundamental equation. Why? It has to, because the real part is controlling the time behavior of the imaginary part, and the imaginary part is controlling the time behavior of the real part. So I has to show up in the fundamental equation, just as it does in Schrödinger's equation, in exactly the same way. Okay. Now, historically, I'll just say this quickly. Well, I'm not the first person to think of this. Obviously, it's kind of an obvious thing to think. Okay, I'll just skip over the time. Well, I'll say two words at the end about time reversal. We're really almost at the end. This occurred, as far as I know, in the literature, first to Heinrich Weber. It's an interesting story here. It's the fourth edition of a book which is based on lectures that Hamilton gave. Hamilton gave the lectures before Maxwell's equations were ever even invented. And each time they released a new edition of the book, the editor could add their own stuff to it. So Weber decides in the fourth edition to present this version of Maxwellian electrodynamics in terms of complex fields. For his effort, this field, this E plus IB thing that I showed you, is given the name the Riemann-Silberstein vector, even though Riemann never had thought anything like it. And Silberstein did the same thing later than Weber. Okay, so that's according to Meisel-Keeling. That seems right. Hey presto, right? Again, what we now get is a first-order differential equation for a complex, single complex field, which is coding up all this information about the reciprocal dynamics, reciprocal first-order dynamics of two fields. Okay? And now you understand why I is there. Okay? You understand why you're getting wave behavior, because you got wave behavior out of Maxwell's equations. You understand how the dynamics is basically working by each field controlling the time evolution of the other field. You understand why I is showing up in the fundamental equations. And so, here's the basic form of Maxwell's equation. And this part only operates, really is going to be a function of the p's and the anyway. Don't need to go through that. All right, so the way you understand this in a Newtonian setting, I'm going to skip this. If that's a linear operator, then you can ask about time reversibility, and I can say this now in 2 seconds, and this is contrary to everything Craig just said. What everybody already knows is that in the context of classical Maxwellian electrodynamics, when you want to, quote, time reverse a state, you keep the E field the same and you flip the B field, right? Keep the E field the same, reverse the B field.
Why?
I'm just saying that's what you do. If you coded up the B field as the imaginary part of this complex field, then that amounts to taking the complex conjugate. So you say, why is the complex conjugate showing up? For the same reason that you do that in a classical electromagnetic theory. You keep this part the same and you reverse that part. Why do you do that? Look at the reciprocal first order dynamics. And I mean, when you say why, what I will show you is, I'll just say, it's easy to see from the fundamental dynamics. That will give you the following situation. If I take an initial state and evolve it to a final state, take the final state and make it an initial state, and reverse the B field, then because the equation is linear, the E field will do the opposite in time, right? It'll go from, as it were, the final state back to the initial state. That's what we wanted out of time reversal. If the movie can happen this way, then it can happen the other way. But the movie only cares about E. The movie only cares about E. Sure, you flip B to get it to work. But as far as things like you want to know, gee, if a bottle can fall off the table and smash to the ground, in principle, can a bunch of unconnected pieces of glass on the ground suddenly jump up and assemble themselves into a bottle on the table? Answer, yes. What am I tracking there? I'm just tracking the positions. I want to reverse the positions. This is also David Albert's conclusion in his book, which is that what you really care about is you pick out part of the dynamics and you want that to go backward. You want to go that in the reversed order in time. You, of course, can't reverse time itself. You then reverse the order of those states with respect to what? With respect to the actual direction of time, past to future. Okay, so this only makes sense in a theory with an actual direction of time. So now I'm at the end. Let me just sum it up. So time reversal doesn't involve reversing time, of course. What the hell could that mean? It means taking a system at a time, spatially reversing P, then letting the system run forward in time in the usual way. If the dynamics is what we call time reversal invariant, it will continue to be characterized by P reversed and Q identical states in the reverse time order as the original system. And now we see that in Maxwellian electrodynamics, you're doing the same thing. E is playing the role of Q, B is playing the role of P, everything time reversed, and in the complexified version, that amounts to taking the complex conjugate. And that is the basic story. Again, you can kind of see how this goes. I go through a little details. That's how time reversal goes in the context of reciprocal first order dynamics. And it's just what you see in Schrödinger's equation. So I think that's the message here, right? The big message, this is just doing the calculations. Here's the real conclusion. The appearance of complex numbers in quantum dynamics has been often characterized as mysterious, or even by Schrödinger himself as unacceptable. There's a pretty simple and direct route to motivating and explaining the fact that the wave function is a complex function and why I occurs as it does in Schrödinger's equation and why time reversal is implemented by complex conjugation. The wave dynamics, in particular simple linear wave dynamics, can be naturally generated by reciprocal first order dynamics. And given a reciprocal first order dynamics with linear dependence of dq dt on P, there's a natural representation of dynamics in terms of a single complex field with time reversal being implemented by complex conjugation of the field. Last point, the electric and magnetic fields were novel ontological postulates introduced by Maxwell and others to account for the evident motion of matter, such as charged particles and magnetized iron. The fields are not directly observable, but their presence is only indicated by the motion of that matter. In that sense, E and B play the role of not directly observable guiding fields for charged matter. The analogy of psi in the pilot wave approach to quantum theory is manifest. The end.
We have 15 minutes. First.
Keep your hands up, please.
Yeah, imagine that was really cool. Just about when you mentioned that I is like a bookkeeping device, it's kind of nothing more than that.
Yeah.
Because it's going to separate like the real and imaginary parts of the city. Does that mean that you could literally do the same job with having a big set of different fonts, and we just stipulate in our maths we can't mix different fonts? The real bit is always
absolutely. Absolutely. It's a typographical convenience. And you could do the same thing, right? You could do the same thing with Maxwellian electrodynamics. You just say, my B fields will be written in italics, my E fields will be written in Roman. A single field is a Roman plus an italics, right? Yeah, and the time evolution of the Roman part is controlled by the italics part, and the time evolution of the italics part is controlled by the Roman part. It's just a bookkeeping.
Cool. That's bonkers. I like it. Cool.
I mean, that's what Schrödinger was scared of. When he said, in that quote that I gave, he said, if I have to keep taking this complex field seriously, then there are really two fields. I'm saying, yeah, good job, Schrödinger. He just didn't like it. I don't know why.
Follow-up?
Just very quick follow-up. It may be a bookkeeping device, but it's a very useful one because complex numbers are governed by the same kinds of arithmetical laws as ordinary numbers. And that's what makes it so useful to represent these two things as a single thing.
Yeah. Yeah, that's, I mean, when I could put the two electromagnetic equations together into one, it's because they both have this Laplacian in it, and you're applying the same Laplacian. And yes, that's also true. Yeah. It doesn't quite work like that in the Hamiltonian case because it's not the same function, right? In the Hamiltonian case, you're taking the partial derivatives, and they can be quite different.
Try and shout. We don't have much time.
And keep it quick, please.
Yeah, great. So great. But I think taking into consideration the fact that maybe I is not just a bookkeeping device. So for instance, in geometric algebra, you can mean the imaginary numbers in terms of geometric entities that are related to orientation in space. And I is something like that. So this is a way in which you can figure out how magnetic and electric fields are related and how they switch when you switch time.
Okay, so
this is more, it seems to be more fundamental than.
Okay, so let me say two words about this. One is that I'm at a certain level very sympathetic to geometrical algebra. What I've been doing for the past 10 years is creating my own alternative to it. It's different, but it's also very geometrical. Okay, so I like the idea. I think that actually the right implementation is a bit different from the way it's done. The other point is, of course, the thing, here's a kind of, I think, a very deep thing. What characterizes I as a number is its multiplicative properties. Yes? I squared is negative. I don't think there's any physical analog to multiplication. Numbers you can multiply. You have an algebra. If you have numbers, you can always multiply two numbers and get another number. And you can talk about the structure of their addition operation and of their multiplicative operation. I think in the physical world, there are clear analogs to addition. Like if I have something this long and have something this long, I can do that and add them up and get the sum. But if I have something this long and have something this long, I can't multiply. I can do this and get an area, but an area is not of the same it's not sort of magnitude that I started with, whereas multiplication is a function that takes 2 of one thing and gives me back 1 of the same thing. So I can iterate it as many times as I like.
You have composition of rotation.
The composition is more like addition, right? I mean, I'm just trying to give you a, so the question, why is I coming up the way Wigner had it, I think he's confused because he's thinking about I in terms of its algebraic characteristics, which just seem, what does physics have to do with that? And the answer is nothing. And of course, if you say I is just a bookkeeping device, you say, I don't care how it multiplies, right? It just has to play the bookkeeping role. Yeah?
So yeah, if I forgot someone, let me know. My list says Oliver, Craig, Alessandro, Paolo, Paul, sorry, and Graham. I leave someone. Okay, Oliver.
Thank you. So the part of the talk at the end went very quickly, and I'm not sure what your answer to Craig's question about B, why did it go to minus C? So to understand the picture, you're taking E and B seriously as 2 real fields.
Yes,
and but there's this fact that when you consider the time reverse, you have to flip the sign of B.
Yes.
And there is this other story that you get where you can understand the transformation properties of E and B and see electromagnetism as time reverse invariant in a 4-dimensional way.
Correct.
So, and in all developments and uses of electromagnetic theory in quantum theory, it looks like it's that F is really the curvature picture that dominates, and the idea that you're taking these fields E and B seriously as the ontology seems less tenable from that perspective. So it's really just to ask you to comment a bit more about
Yeah, so let me give you, again, I mean, there are eight different talks I could give here. You just tickled me another one I could give. So let me give you the quick answer. And it's one we already know. I was trying to get you into this by making an analogy to classical Maxwellian electrodynamics, because everybody's kind of familiar with it, and you can sort of see how it works very easily. What we know in quantum theory, what we know for sure, is that A, E, and B, because you don't put E and B in the equations, you put A in the equations, you put the potentials, you put A and phi, right? The scalar and vector potentials. That's what's doing the physical work. You need that to give the Aharonov Bohm effect. So how do I understand the dynamics of A and phi? Reciprocal first order dynamics. Phi is a certain kind of field. We would say a scalar field. I call it a zero field. A is a different kind of field. Normally it's called a vector field. I call it a one field. Write down fundamental reciprocal dynamics where phi controls the development of A controls the development of phi. But we know we have to do that. And we know all the pictures. I mean, if you start with a classical relativistic electromagnetic tensor defined essentially at the level of E and B, we know that's the wrong way to begin to do quantum mechanics. We need A. And furthermore, I'll just, as a point, if you do it the way I do it in discrete spacetime, and you start with A, then you get that the divergence of B is zero, no magnetic monopoles for free. It's a purely mathematical consequence of the chain of definitions.
Great. Thanks, Tim. I just wanted to comment that if you use the other classical Schrödinger equation, not the one I talked about this morning, but the Köppen-von Neumann one that's linear, then there's this great consilience between. So I think exactly the same thing as you just said about where I comes from, and so you could mimic the entire story the same way. So you'd have two equations, one for R, one for S. I want to combine them and into one, and then so it's more compact, and then the I pops out there. And then the crucial thing that's interesting is that if I do that classically, I can do it, but it's kind of bullshitty but in the quantum case, what's not so bullshitty because what's interesting is when you have those two equations, R and S are coupled.
Yes.
In the quantum case, and in the classical case, they're not.
Yes.
And so then, that's sort of like, to me, if you think what's the basic difference between the two, it's that you have those two first order fields.
Yes.
But in this case, like in E and B, they're coupled.
Yes.
And because they're coupled, then it makes sense to put them together into this one thing. also because decoupling, then it's like arbitrary about how to divide the real and imaginary parts.
Right.
And so in one direction it makes sense, and voila, the eye pops out.
Yeah, I mean, I agree with that. And I should also say, look, for expository purposes, and also because I haven't worked it out yet, I just thought was asking you to think of psi as having a real and an imaginary component. Now, Craig is quite right, because it's a complex field, you can think of it instead as having, again, 2 degrees of freedom, an amplitude and a phase, and divide it up that way, right? And then try and get, again, reciprocal first-order dynamics between amplitude and phase, for example. And that might be the right way to do it, right? Because then if you take the state space for the phase as being closed, okay, you can get some stuff automatically. I haven't thought any of that through. I think that's a perfectly good way of thinking about it. All of that is under this big umbrella of reciprocal first-order dynamics. So I think you're so. I mean, the thing I disagreed with conceptually when you were doing was saying, well, now the classical equation pops out with the quantum potential. But to me, that's going the wrong direction. I want to get away from Newtonian dynamics, right? So maybe it does, but I don't think that's a good sign. I think that's a bad sign. I want everything to look. It's more and more looking like Maxwellian electrodynamics, not like Newtonian. But yes, I agree. You can, and I need to think through, which I haven't done yet, what happens if you reformulate this in terms of where amplitude and phase rather than in terms of real and imaginary parts. Obviously, there's a way to do that.
Yeah, thanks. So it's the same question in some sense of Oliver Cooley, but I'm not sure I understood your answer. So you were discarding all these diffusion equations over your scopes because they were not fundamental.
Mm-hmm.
And from your answer, it looks like you will have to go to the electromagnetic potential. Mm-hmm. That's a fundamental equation.
Mm-hmm.
And now I'm not sure how, so as I saw the game, how it was going is that we use an analogy from electricity magnetism
Mm-hmm.
with complex and imaginary part of the wave function. But now I don't see how you could do that now with the electromagnetic potential.
As I said, I mean, I'm asking you to think of this at a somewhat high level of abstraction. I mean, I'll just say something that's going to sound technical, but maybe it'll give you the idea. In the way I'm developing this, it's kind of alternative to geometrical algebra. You have in a 3-dimensional space, you have 4 different types of fields. It's basically a field ontology. So, I mean, one way to begin this is to say Newtonian mechanics is fundamentally a particle ontology with second-order dynamics. Electromagnetism is fundamentally a field ontology with first-order dynamics, right? I mean, they're as different as they can be. Now, in the way I'm doing it, there are actually 4 different kinds of fields in principle. 0 fields, which you could think of like scalar fields defined on points. 1 fields, which are like vector fields defined on lines. 2 fields defined on areas. Those are what we call pseudo-vector fields. 3 fields defined on volumes. Those are what we call pseudo-scalar fields. It's just kind of a weird accident that we live in 3-dimensional space. So just having scalar and vector fields gives you enough resources to do physics. It's just a lucky accident. Anyway, in this setting, to do first-order reciprocal dynamics, you need 2 fields that differ from each other by 1 level. In electromagnetism, in classical electromagnetism, in my terms, it's a 1 field and a 2 field. The electric field is a 1 field, the magnetic field is a 2 field. You take a spatial, the natural spatial operator takes you up or down a level, right? So what corresponds to the curl? It's called lift and drop operators. So what I need are 2 fields that differ by 1 level. Standard E and D electromagnetics chooses a 1 field and a 2 field. When I do it in terms of potentials, I drop them both down. I've got a 0 field and a 1 field.
You mean form, like 1 form, 2 forms?
No, they're not. You don't understand these words because they're in this entire discrete space-time setting that I've been working on for 10 years. It's there. You will see similarities to the theory of forms. Let me say a word about that. The theory of differential forms exists because you're using a theory in a continuum, and you've got to take intervals. So you need to integrate against something. That's why they're differential forms. I'm doing this in a discrete setting. You never take an integral. You just add and subtract stuff. They're just difference operators. I don't need any differential forms. But there are clear mathematical similarities between what I'm doing and what shows up in this theory of differential forms as well. So you can sort of think of them like one forms, zero forms, and one forms. They're not. What's important is that they differ by one. Right? To get this reciprocal first order gadget going, you need two things that differ by one level. And the lift of this guy is going to control the dynamics of this guy, and the drop of that guy is going to control the dynamics of this guy. And you can do that just as well with the potentials as you can with these. I know that's very fast, and there's a million things I would have to explain. But there is a picture. There's a pretty well articulated picture.
Okay, I apologize with Graham, and well, I apologize less with Alec because